I will be talking about spectral density deconvolution from group data. So if you have any questions, during my presentation, feel free to interrupt me, after I finish the slide and before moving to the next slide. So here, the group data model assumes that the variable y we observe is the sum of PID variables, okay, where the mother variable has Lebesgue density, okay? It is assumed that we observe a random sample from y. The aim is to estimate the density of x from those n observations, okay? For any random variable z, we're going to use subscript fz, ft to denote the characteristic function of the random variable z. Sometimes I will be using, the Fourier transform, being understood that those are equivalent up to scale. Okay. Can you guys hear me?
Yes, we hear you quite.
Perfect. Okay, perfect. All right. Now, some important applications of the group data model. So the first application arises in labor economics, where X represents the transitory income shock. Basically, we work on a pile data model. And so the first difference in the error term is the Y, basically. And so in that case, P is equal to 2, okay? The second important application arises in financial engineering, when one is interested in when X represents the unobservable high-frequency return of an asset whose log price follows a levy process. Okay, so this permits basically to recover the high-frequency return when the latter cannot be observed due to, for instance, microstructure noise or low liquidity. Okay. The third application, which is in fact a slight extension of the methodology I will present today, is the decompounding model, where basically here P is not a known positive integer. It is basically a count variable following a certain distribution, and usually we use the Poisson distribution. Okay, I will be briefly covering those extensions for the decompounding model at the end. Okay. Now, what are the available methods? Well, basically, when the characteristic function of X is real valued, one can estimate the target density using, the classic inverse Fourier-based method. This requires a non-vanishing characteristic function, which precludes, compactly supported distributions, as well as convolutions based on these. But even if this condition is satisfied, the mean integrated square error has a rate of convergence which should be subject to a curse of dimensionality with respect to P. Okay, and so this is not very appealing with data of the size typically encountered in economics. For instance, if you want to estimate a high frequency return from hourly data using the hourly prices, you're going to have a P which will be very large if you want to get a 1 minute data, for instance. So the proposed methodology here basically solves those problems, because first it can accommodate, as we will see, virtually any symmetrical distributions for X, much broader class. And also it produces a faster rate of convergence. And in fact, a rate of convergence which will be substantially faster when P is large. Okay. Now I'm going to use some notations to keep things concise. So if you guys are of a math background, this should be straightforward. I'm going to use the norm, the weighted norm, with K being the weight function. Okay. With respect to the square integral. When K is equal to 1, that's the classic square integral. So I'm going to use no subscript, just the norm symbol. The L2K space, the space of square integral functions with respect to the K function, the K weight function. I'm going to use many times I'll be speaking about a function, having subalef smoothness. Okay. Well, this will refer to the subalef smoothness with respect to the L2 norm only, since it's what we use in statistics. So, for instance, when S is a positive integer, this basically is the space of functions having S weak derivatives, which are square integrable with respect to the Lebesgue measure. For the convolution symbol, I'm going to use the classic symbol with a star, okay, to convolute two functions. And I'm going to use for the autoconvolution operator, I'm going to use A on the subscript n to denote the n-fold autoconvolution operator when you autoconvolute the same function n times in a row. Okay? All right. Now, to appreciate the estimation technique, I will present. One must understand that the target density solves a nonlinear Freedom integral equation of the first kind. Okay. So this estimation problem is ill-posed because the Frechet derivative of the autoconvolution operator is a compact Hilbert-Schmidt operator with a spectrum, contains 0 as a limit point. And so, and in fact, the degree of ill-posedness augments with the smoothness of the autoconvoluted density, and so therefore with the p, the dimension. And so therefore some regularization is required to estimate the target density from data, because otherwise the solution will not be continuous in data. Okay? To identify the target density, we need the characteristic function to be real valued. Okay? Now, to use the spectral theory, we also need basically the target density to be part of a subset of some Hilbert space with elements admit a Fourier transform. Therefore, we're going to assume basically that the target density belongs to basically the space of even densities, okay, whose weighted square integrable norm is smaller than some known constant, okay? Using a specific weight function, which must specify certain tail conditions, so that automatically this parameter space will be a subset of L1 integrable functions with respect to Lebesgue measure, okay? As we will see, the choice of this weight function is not really plays no role in terms of the consistency of the estimator. You can use pretty much any weight function satisfying those tail restrictions. However, to obtain a good rate of convergence, you're going to need to specify to use a judicious weight function. Okay. Now, this is the parameter space if p is an odd integer. Now, if p is even, we're going to have to assume an extra condition on the Fourier transform, which will need to be non-negative. This arises because the power function, x raised to the power of p, is not injective if p is even. Okay, and so we're going to have this extra sign restriction on the Fourier transform. Okay.
Sorry, there is no mistake here. Sup yes. Less than infinity. Is it correct? This ratio. Mu is positive and
yeah, the weight function.
Is it correct inequality? Just check it.
On the weight function?
Because p is a density, something like
that. No, p is not a density. P is not 1 over p is a density, if you will, up to scale. P is not. It's a function with tails grow. 1 over p is a density, if you prefer.
What is a density, sorry?
If you want to relate that to a density, 1 over p is equal to a density up to scale. That's what this says, basically, with tails are sufficiently fast declining. But p is a polynomial. P is 1 plus a power of x to something. It must grow. Okay?
Okay.
Yeah.
Okay.
Yeah. So 1 over P, if you will, is a density up to scale. Yes.
Okay.
Okay. Yeah. So yeah, so basically it's a good transition to your question. So basically, we're assuming that the tails of the target densities are sufficiently thin, which is mild because we don't even need to have a first moment, but we need at least some fractional moment. Okay? All right. Now, to understand the estimation, observe that, that's what I discussed previously. So the target density solves this autoconvolution integral equation. Now, one possibility is to estimate the density from the analog. Okay, the case would replace the density of y on the right side by its non-parametric estimator. The problem is that this non-parametric estimator will converge at the non-parametric rate, which will be slower than root n. Now, one can perform an additional smoothing step to speed up the rate of estimation for the analog, because if you convolute a density with a function, you get an expected value, which therefore can be estimated at the parametric rate. So I convolute by a density g on both sides, and under mathematical conditions concerning the g, this is equivalent to solving this new nonlinear integral equation when m is a new operator, which is known basically, and q is unknown, but q is an expected value. Okay, so basically our proposed estimation is based on the analog. Okay, now to estimate the analog, we're going to use the sample analog for q. Because q is an expected value. Okay, we're going to introduce some weight function on the range pw. Okay, which must be chosen by the researcher, must satisfy some mild restrictions. And the estimation is based on the analog when we minimize the distance as implied by the identification, but we add a penalty term, okay, using a ridge sequence, an, which must vanish as the sample size approaches infinity. Now, using this ridge, basically, sequence regularizes the solution, which will then be continuous in the data. Okay. Now, this is called the Tikhonov estimation regularization technique. Okay, which is very convenient in the context of this problem, which is a nonlinear Fredholm integral equation. Okay, because with a nonlinear integral equation, we do not know the spectrum of the operator. Okay, so we cannot use the other techniques such as the spectral cutoff technique when you keep only the eigenvalues which are, greater than a certain level. So therefore, the regularization is embedded directly within the objective-based minimization problem. Okay. Now notice that by definition, the estimate you will obtain from data may not be a density. Okay, it's just we don't impose restrictions on the density on the sign of the function. However, you can impose those restrictions on the parameter space. That is, you impose that the function must be positive and it must integrate to 1. Okay, well, in that case, that will not modify the results of this paper because the parameter space still remains closed and convex subset of some Hilbert space. So, however, this will introduce numerical difficulties when implementing the estimation, because you're going to have to use on a constrained parameter space, which is not obvious to implement. Okay.
May I ask you?
Yes.
On this stage, is it important that f is an odd function? You told us in the beginning that you will work only with odd densities.
Even, yes. Even densities. Yes, yeah.
And on this stage, so this is not important at all.
It's embedded because you see argmin f in u. You see here.
Okay.
You see, okay. That's my parameter space. Okay. U was defined previously. I'm saying if P is odd, you have that parameter space. If P is even, you choose that parameter space. Okay.
Mm-hmm. This is the difference. Because you explained to us something about numerical complexity of this task. And
here, because of this here at the end, the restrictions. Yeah. Yes. This complicates the numerical implementation, because if you have the first parameter space, even densities, square integrable, you can use the Hermite basis. Hermite basis, automatically the coefficient, if it's even, you're gonna keep only, you're gonna have one, some coefficients will be zero. It's gonna alternate, right?
I see.
So it's gonna be easier, yeah. But technically you could do it, yeah, with a. Does that respond to your question, Vladimir?
Yes, thank you.
Okay.
Just one question. I remember my very old paper when I estimated also spectral density with the help of Tikhonov regularization method.
Yeah.
And I think that it's very close to what you are doing. Maybe functional spaces are different.
Yes.
But methodology is the same.
Yes, it is the Tikhonov. It is the Tikhonov method.
Known very well for a long time. Yeah.
Yeah, but it's Tikhonov with nonlinear, with a nonlinear operator. So you don't see basically and when the operator is unknown, so you don't see basically there's no analytical formula, analytical expression when you estimate the density using as a function of the eigenvalues, because it's embedded within the objective.
I received also the rate of convergence, which you indicated at the beginning, for P equal one dimensional case.
I think
interesting.
Yeah. You can. Yeah. I know what you mean. Yeah.
Okay. Thank you.
Yeah. Thank you. All right. So you minimize that, and that's the estimator, Tikhonov estimator, basically. So the assumptions, I already introduced the parameter space. So here, the weight function of the range can be any measurable function that is strictly positive and uniformly bounded. Okay. Now, it plays no role, in terms of the consistency result, although the interpretation of the smoothest conditions to derive a good rate of convergence will be influenced by the choice of the weight function on the range, PW. And this will be explained later on, okay? Considering the function G, you just need to select some even bounded Lebesgue density whose Fourier transform vanishes on the Lebesgue null set. That's sufficient. So for instance, you can have convolution involving symmetric uniform densities that would work, triangular distribution that would work, and of course all the symmetric stable distributions that would work, okay? And concerning the rich sequence, it must converge to zero at a certain rate. That is, you want that to, because if it converges to zero too fast, you won't be able to solve the ill-closeness, okay? So although those mild conditions, we get an estimator which is consistent in our metric, which implies that it's consistent in the classic L2 metric, that is, its mean integrated square are consistent, okay, due to the properties of the weight function, okay, because it's a stronger metric. Notice that this consistency result does not require the Fourier transform of the target density to be integrable, absolutely integrable, nor the Fourier transform to be strictly positive, okay? This is not needed to get the consistency. And therefore, we can accommodate a much broader class of distributions if one is only interested in deriving consistency. For instance, densities which are unbounded around the origin, such as the Linux distribution. I don't know if I pronounced that correctly. Basically, it's a density that is unbounded around the origin. That would work. I heard a question in the background, perhaps? No? Okay.
And of course, have a rate only tends to zero.
Yeah, not yet. I'm going to cover the rate in the next theorem. Okay? Yeah, because I want to distinguish. You see, you can get consistency under very mild conditions. And then we're going to see that we're going to need to strengthen those conditions to derive a rate. Okay? And of course, this implies that from theorem 1, you can estimate functionals involving the density. For instance, the CDF under biotechnical conditions concerning the function h. So the CDF can be estimated pointwise, for instance. again under extremely mild conditions. Now, to derive the rate, we're going to need to introduce extra smoothness assumptions, and we're going to have to introduce some notations. So D, basically, that's the Frechet derivative of the of our operator M, okay? D star, that's the adjoint, okay, operator. And I'm going to introduce the L constant, which is a strictly positive constant measuring the smoothness of this nonlinear operator, okay? So for instance, with a linear operator, which is not the case here, L will be equal, can be any arbitrary small number, close, okay? But here it's linear, it's nonlinear. So basically that constant, exists under our previous assumptions, but it's unknown. And the smaller the value of L, okay, and the smoother the nonlinear operator, okay? All right, so the first assumption we need to derive a rate is that the set of points where the characteristic function of the x vanish is a null set, so isolated zeros, okay? So this is a bit more restricted, but usually this can accommodate, fairly still a broad class of distributions, okay? This permits basically the operator to be injective, the Frechet derivative to be injective, in which case we can use a spectral theory to derive the mean and the variance of the estimator. Now, under this assumption, we can there is a singular system decomposition for the operator, the Frechet derivative D, which implies that basically we have some orthonormal sequence and some eigenvalues, and an infinite sequence of values containing 0 as a limit point, okay? And those basically square lambdas are summable, okay? So they converge to 0 relatively fast. And we do know also that the target density belongs to our weighted Hilbert space, and therefore there are chi j's coefficients, which are the generalized Fourier coefficients, which are summable and converge to 0. Okay, and so basically to remove the bias from the regularization, we're going to need those generalized Fourier coefficients, the chi j's, to vanish, to decay to 0 towards 0 sufficiently faster than the eigenvalues, okay? So that's next. We assume there is a constant beta such that the summability is satisfied, okay? The second condition basically is mild in the sense that if the first condition is satisfied, then automatically the second condition will be satisfied if you take the function g to have basically a supremum which is small. So basically you take a density of a random variable whose variance is large, and this will be satisfied. Okay, now let's to develop some intuitions about the source condition here, okay? We can focus on specific case, basically, and see that the decay beta relates to the tail decay of the weighted signal. Weighted signal here refers to fx weighted by the weight function, okay? And that's the Fourier transform. So, for instance, if the function pw you take on the range, is integrable, for instance, the density, then the decay beta, when you take 1/2 or if you take 1, okay, those two cases, well, essentially requires the weighted signal to be smoother than the autoconvoluted density in the Sobolev sense, okay, so a bit smoother in the sense of root derivatives. Now, if you take no weight function on the range, pw equal to 1, which works according to the theory, then the decay, the minimum smoothness condition, the minimum decay, that is beta equal to 1/2, is ensured if the given integral this ratio is integrable. Okay, so which basically requires a non-vanishing characteristic function, notably. Yeah. So let's look at some specific example, for instance, to develop why it works. Let's take normality, okay? Let's assume the target density is a normal density, okay? Symmetrical, because we want symmetry. Then the minimum decay, beta equal to 1/2, can be ensured if you use a weight function for the reference space based basically on the reciprocal of a normal density whose variance is larger than the variance of the target density. Why? Because if you do that, eventually you're going to render the product of the two functions, the weighted signal, which be extremely smooth. Okay, and therefore you're going to have a larger variance in effect, and therefore the Fourier transform, which will vanish much faster than the autoconvoluted density. Okay, for instance. Okay, now of course this is just a pedagogical example. In reality, we do not know whether we have normality or not. Okay, so how do you choose this weight function to ensure that we have smoothness? Well, I provide a little sufficient condition which can help a researcher which can provide some guidance in applied works for people who want to use some feasible estimation where the weight function will be estimated, accurately, and therefore providing a way to mimic the source condition we need to remove the bias. This is done in the case of a full support, but this can be generalized if the density has a bounded support. Okay, so suppose we have a function which is fully supported on the real line density. Suppose that the first moment exists, okay, for the variable, okay, slightly more. Take a function g, which is essentially a fat tail density, the density of a fat tail distribution, basically. Then the decay 1/2 is ensured if you take this weight function up to scale equal to this ratio. The numerator is an expected value, so that can be estimated at the parametric rate. The density in the denominator, of course, that's the unknown density, it's unknown, but from theorem 1, we can estimate that density consistently under mild conditions. So that suggests, therefore, using a first stage estimator, getting a consistent estimator for the density, plugging that, getting a feasible version for the weight function, and then producing a feasible Tikhonov estimator. Actually, it's what I did, actually, but I didn't have time because it's very time-consuming numerically. But what it does when you do that, in practice, it helps with the bias. So it really improves the bias a lot. But it's very computationally very demanding. Okay. All right. Now, so under those assumptions, basically, and if the ridge Tikhonov sequence AN vanishes at a suitable rate, you get the following rate. So notice that there is some saturation effect, okay, because you cannot get a rate, an integrated square error rate faster than 2/3, okay. Notice that this, I will talk briefly why this is the case, okay. Now, but as given here, this mean square error rate is faster than the optimal rate for the Sobolev class derived in Meister, okay, 2007. And in fact, one can show that it is at least p over 2 times faster than the rate you would get with a Sobolev class, okay. And of course, this improvement results from the extra knowledge we assume concerning the tail of the target distribution, something which is not assumed in Meister paper. They only assume on the Sobolev space. They work on the Sobolev space, and that's it. Okay, so by imposing extra tail restrictions on the target distribution, we can, in theory, improve the speed of convergence. Okay, and why? Well, because for any p, however large p might be, we can create a weighted signal which is smoother than the noise. Okay, we can overcome the weighted signal with a weighted signal which is smooth. Okay. All right. Any questions? Okay. Now, as I said earlier, the estimator suffers from saturation in the sense that the fastest possible rate is equal to 2/3. Okay. This arises because the Tikhonov regularized solution is an infinite dimensional parameter. Basically, it retains all the singular values which precludes bias reduction when high smoothness is present. Okay, there are other regularization technique, for instance, like the cutoff technique, when you remove the angled values which are too small. In that case, you don't have that saturation problem. The smoother, the decay of the Fourier coefficient, and the faster the collapse of the bias. Okay, but this is not the case here because the cutoff method is not usable because the operator is nonlinear. Okay, so so the angle values are unknown. Okay, and again, this result implies that any functional involving the distribution can be estimated at the same mean square error rate. Notably, one can estimate the CDF, okay, of the density pointwise at the same rate. Okay. Any questions? Okay. Vladimir, can you hear me?
Yes, I hear you quite well. I don't have.
Perfect. Okay. Now, possible extensions. So basically, now the first possible extension, that's easiest extension, is when the parameter p is unknown. Okay. Now, in that case, there will be a straightforward extension. It's relatively easy to extend if you assume that the support is compact and known. Why? Because if you convolute p times, automatically the convolution will extend the tails, the boundaries, right, by a multiple. And so therefore, you can easily identify the unknown parameter p using basically the extreme, the boundaries of the support of y, okay, right? Right. So you can usually, there are a variety of techniques to estimate, the support of a continuous random variable. So assuming you have that estimator for that parameter p, you can plug that in the first stage and then use a feasible Tikhonov estimator when the p is replaced by its estimator, basically. Okay. So what you will get at the end, if you use that, is that because assuming that the p converges at a non-parametric rate, which is usually the case for support estimation, and the density is non-vanishing, you can estimate basically at a fraction of the previous rate I described. Basically, why? Because basically the rate at which you estimate the p will create an error size dominating the other sources of error, right? Because previously the analog was estimated at the parametric rate. This is slower with the estimation of p, okay? And the estimation will not be in the sense of the expected value, it will be instead of the convergence in probability, because the expected value of p hat may not exist. So you derive a rate of convergence in the L2 metric, okay? Now, concerning the decompounding model, so here we don't have p, but we have a count variable n, which is a discrete variable having support 1, 2, etc. Okay, positive natural numbers. If we assume the classic, condition that the count variable is independent with a variable x, we can derive, a new nonlinear integral equation, which is a weighted, basically, series of nonlinear operators. Now, the case where the distribution of the count variable is known has been, studied in Delormesti, Morezona, and Panov. Okay, so you can identify the target density. Okay, using the inverse Laplace transform. Okay. Now, in that case, we can use the previously exposed Tikhonov methodology. We just need to rewrite the operators. Okay, so you rewrite the operator m using basically the series of involving nonlinear autoconvolution operators, and you redefine the Fresher derivative using an infinite series. But that would be the exact same thing in terms of the nature of the assumptions. Okay, so again, and the result of using that would be, that you would get the same qualitative improvement over the classic Fourier transform based technique. That is, if the target density is not smooth, you know, you can derive a much faster rate of convergence by using the appropriate, weight function, etc. Okay. Now, the more challenging situation arises where the count variable has an unknown distribution, and it's relatively, it's a very challenging problem because one must identify two infinite dimensional parameters. Okay, the distribution of the count variable. Okay, typically there's no limit on there's no upper bound, so that's an infinite dimensional parameter, and the target density. So you have two infinite dimensional parameters to identify. Now, assuming that you can identify, and estimate the distributions of the distribution of the count variable in the first stage at a certain rate, uniform over all the points in the support, well, then you will have to basically use a truncated version of the nonlinear operator I presented earlier. Because if you use the infinite series, that may not exist. Okay, so and basically the speed at which the count distribution, the PDF values, okay, the values of the PDF of the count variable decay, that speed will determine the rate of convergence because that will create an extra bias basically from truncation. So if it decays very fast, you may get the same rate as previously. If it decays very slowly, you may get a very slow rate, very slow bias reduction, and which will dominate the previous bias we derived with the Tikhonov, technique, etc., etc. So yeah. So some Monte Carlo experiment to get some ideas. So here we have we use sorry, it should not be J, should be P, okay? P is equal to 3, okay? And X is basically the convolution of a normal variable and uniform variable. Notice that by construction, the density of X has a Fourier transform which vanishes, okay, and which has sign oscillations, okay? So it's fine because since we have 3 count, P is equal to 3, we can use, we can have sign restrictions as we learned during the definition of the parameter space, okay? Concerning the reference space, here we'll be focusing only on consistency, okay? So I'm going to use the simplest probably reference space, 1 over x to the square, and no weight function for the range, so PW is equal to 1. The function g is the Laplace density, okay, with a scale parameter equal to 1. And I use the regularization sequence satisfying the condition for consistency, okay? The estimator is computed with the Hermite basis, with series lengths truncated with 50 terms. It's relatively easy because it's explained in the paper. You can approximate the weighted density with a Hermite basis since it belongs to L2, square integral, okay? And so you just select random values and within the conditions, and you can iterate and search for the minimization solution. The objective is minimized using a random search algorithm over a feasible parameter space. And remember, you have to impose a bound on the square integral. C, that's the upper bound. Well, that's the way you would do it in practice, since you don't know what the unknown density, is unknown. So you can assume for simplicity that you start from normality, okay? You get the maximum likelihood estimator for the target density, or you can use some other symmetric stable density. And you use 4 times the norm, okay? So that creates the bound, okay? Because typically, if the target density is not super different in terms of shape to this assumed parametric density, 4 times the square integral typically gives you, a fair safety net in terms of this upper bound, okay? And then we iterate using the, random search algorithm with a budget of 1,000 iterations, okay? And we start from the maximum likelihood estimator, okay? So I'm going to derive some quantities. So it takes a lot of time, to use to compute the estimator. So I use only 200 replications. Okay. We're going to use the mean square error, which is the L2 norm, the bias 2, which is the bias square, and the variance. Okay. So those are the results. So you see that we use 100 observations and then 400 observations. So what you see is that, you know, for a given sample size, there's a trade-off between the bias and the variance when you increase the rich sequence, okay, as measured by the CA constant, okay. So the larger the CA, the more you regularize, and therefore the higher the bias, okay. And so, but the lower the variance. So there's a trade-off. And when you increase the sample size, multiply 4 times larger sample size, the mean square error decreases, okay, which is you know, expected from the theory because it's supposed to be consistent. And the bias vanishes and the variance vanishes, okay. Now what you see is that basically here, according to our, of course, the regularization Tikhonov sequence CA, the variants are not very different whether you use a large rich parameter or a low rich parameter. Okay, the main difference pertains to the bias. So it looks like the estimator is more sensitive. The bias will be very sensitive to the regularization sequence. If the sample size is large enough, the variance will not be greatly affected. Now some graphs. Okay, so 100 observations. So you see the shape is captured fairly well, except on the tails, okay? The higher the regularization sequence and the flatter the expected value of the estimator, okay? So you're gonna be more biased, okay? And eventually, if the sample size is large enough, the problem we had on the tails will eventually disappear and the tails look a bit more closer to the, you know, true density, okay? Just a conclusion. So I've presented the method to estimate the density from group data. Consistency has been derived under very weak conditions. The rate of convergence is not subject to curves of dimensionality, okay, with respect to the count parameter, provided the reference space is well chosen. Okay, so the key is to choose a judicious weight function, which can be informed from the first stage estimation, as previously explained. So there are two natural questions. First, you know, the optimal choice for the rich parameter, Tikhonov parameter. That's important in finite sample. And the second question, the finite sample properties of the feasible estimator based on a weight function that is estimated consistently in the first stage, as described previously. At first, it will be good to examine using Monte Carlo simulations, just like I did. But if somebody has more time, you can see what's going to happen if you estimate the weight function. Okay, my personal experience showed that it reduces the bias tremendously. Okay, it helps with the bias, which makes sense because the source conditions are supposed to, you know, remove the bias. That's what the source conditions are about for, you know, Tikhonov regularization. It's about bias removal. And this concludes my talk. Any questions?
May I ask you about the case of unknown distribution of n? So,
Yeah.
do you have any ideas how you can extend this methodology to the case of unknown n?
No, I mean, actually, you know, as I said earlier, if is unknown, we have to identify, we have two infinite dimensional parameters, right? Because if you look at the estimator is this, okay? This is equal to the to the density of y, okay? So you have the pj, the probability of the count equal to 1 equal to 2, etc., okay?
Yes.
And you have the f, the density, okay? And so it's not obvious. I don't see any obvious ways to. I mean, the strategy would consist of identifying the p's in the first stage, okay, and then plugging that in, right? That's what I suggested, to have a feasible version. You could do that, but how do you identify P if you don't know F? So, and you cannot use what I did when P was a known integer, because if you have a support restriction, if you convolute, eventually you're going to extend up to a certain point, right? So this you can use when P is a real unknown constant. You can use that approach. You estimate using the boundaries. You estimate the boundaries of the support of Y, what you observe, right? And but when you have a random variable, you can try to mimic that, but you will have to conditional on each P. So you say, okay, you would need maybe an external variable, an external variable that would have predictive power. That is, that N is equal to something if that other variable is equal to that, or something like that, If you have that, you can mimic what I did with previously with the support was compact. But do you have suggestions?
So if you use some parametric conditions on the distribution.
That's another question. Yeah.
But a non-parametric case, yes, it's completely another story.
Yeah. So a parametric distribution, that could be easier. In that case, it would be a semi-parametric estimation problem, right? The PJ will be known up to some parameter, and in that case, you will need to identify, you can impose perhaps some monotonicity restrictions. Something like that. Yeah, it would be much easier. Yeah.
Okay.
Yeah, parametric assumption would be probably the way a practical way to solve that. Yeah.
So the classical task is to use parametric assumptions, for instance, to assume that N has a Poisson distribution, and simultaneously estimate the rate of this distribution and also the distribution of one summand. This is a classical task. It was solved many years ago, but afterwards only a few papers were devoted to this problem. I think that it's not so easy. And the question of identifiability is, of course, quite important, and we tried to somehow fix this problem in our private communication.
Yeah, parametric assumption or a support restriction might help also. A bounded support, a known support for X.
I see. Okay, any other questions to Mr. Krief? So if we do not have any questions, I would like to thank you very much for this talk. Let me stop.